Welcome. So let's continue this lengthy exercise about vector field flux and also the important Gaussian divergence theorem, which comes into play at the end. Well, we've been considering this little cube here as a closed surface, and we've already found out the correct radius vector functions for the first three of its faces, which are numbered in a way you see here in the sketch. Number one is the back face, number two the left face, number three is the bottom face, and now we're still missing corresponding radius vector functions for faces number 4, 5, and 6. As you see, there's a close, well, you could say connection or relation between the back face and the front face, for example. If you compare these, so face number 1, the back face, is pretty much the same as face number 4, which is the front face. What do we have to do to transform this radius vector function now to a valid radius vector function for the front face? Well, the answer is quite simple. 2 steps. Firstly, it strikes you that they are parallel. 1 and 4 are parallel, but face number 4 has a replace, or you could say a displacement in the positive x direction. It has a displacement for a distance of 1. That's what I wanted to say. Okay, so if you just take face number 1 and displace it for a distance of 1 to the positive x direction, you get face number 4. So almost all we have to do is to replace this 0 for x against number 1, a value of 1 for the x coordinate. That's the first step. The other step is, interestingly, we have to exchange the u and v variables against each other. Why is this so? Well, the reason is simply the fact that, look at n1, the normal vector of face number 1 must point to the back hand side, as we found out. And that's, or it must point, well, away from you, prospectively. Why? Because all these normal vectors should point outward of our body here, of our cube. That's the definition of normal vectors, so that the flux is calculated correctly. If it's an outward flux, it should be positive, right? So it means that the normal vector for face number 4, which is not to be seen here for reasons of clarity, it would be too much, okay? It would have to point towards us. So it would have to be this one with changed signs. It should be the vector 1, 0, 0. And in order to get it correctly, you see that it arises formally, mathematically, by building or constructing the vector product between the 2 tangent vectors. First one, direction of u, other one, second one, direction of v. In order for this to work correctly, we have to exchange u against v, so that in the end, the normal vector points toward us. So that's 2 steps. Replace 0 against 1, and then exchange u and v against each other. That's what I'm doing. Just look here. 0 v u gets replaced for 1 u v. The same holds for, I needn't explain again, okay, the second phase and fifth phase, and also phases number 3 and number 6, bottom phase, top phase. They all have a similar connection to each other. So if you just keep in mind shortly, the function for phase number 2, this stands for surface part 2, okay? u0v must be replaced against v1u. Yeah, that's it, okay? So u and v exchanged in order for the vector product to change its sign, and 0 replaced against 1. So we get v1u, and this is what you see here for S5. Then, next, or last one, just replace vu0 against uv1, and that's our radius vector function for the 6th phase of our cube, which is the bottom face. Now we are done with this, and then, well, look here, for the second part, of course, to calculate the total flux, which is formally well, a double integral over a closed surface of the vector field. As you know, as always, we have a differential area vector which points in the normal direction outside, as described, and this is our vector field, well, as seen before. And so that's what we have to do. Remember, in order to express everything using our auxiliary variables u and v, this will get an iterated integral over u and over v, where we must, before we start, replace every occurrence of coordinate x inside the vector field against the corresponding expression in the radius vector function for the corresponding part of the surface. Now, this has to be split up in 6 parts, which we have to sum up, of course, because our different faces of the cube are described differently. Well, so in the first step, we have to replace any occurrence of x here against 0, any occurrence of y against v, and any occurrence of z against u. That's what we do. And well, let's just do it in mind now. So 0vu have to be used instead of x, y, z. So we get 0 squared, which is 0 here for the first vector component. Here we get 0 times v, which is also 0, and 0 times u is also 0. Why? Because everywhere there is a factor of x. In other words, it means that the vector field vanishes in the total region of the back face of this cube. Why does it? Well, actually, this vector field disappears everywhere in the drawing area. In other words, everywhere in the YZ plane. So that's no surprise. We don't have a vector field at all, or in other words, it can't generate any flux because it, well, you could say it just doesn't exist, or there's no flow here going on, right? So that's quite a simple situation. Then moving on to the second face of the cube, which is the left side here. Well, we find out differently that this time the x component is not necessarily 0. Well, at some points it is, but not everywhere. So it's replaced against u. But now this time the second component is 0, and the third one is v. Look again, u0v for x, y, z. It means we get u squared here, then u times 0, which is 0 again, and u times v here behind. So that's how we proceed. Well, let's look at the third one also, vu0 instead of x, y, z. Well, v squared, yeah, v squared, I forgot it, vu0, right? Yeah, v squared, then v times u, or uv, anyway, and then what did we have? vu0, so this is v times 0, so the third component of the vector gets 0 in this case. So that has to be done all the time for all the different faces, and that's why it gets a little lengthy here. So you remember, this was the fact that on the first of our faces numbered here, the vector field vanishes, and on the second face it doesn't vanish, but don't forget, you always have to multiply scalar product with the, well, you could say the correctly calculated normal vector, which, as I told you last time, also carries the correct Jacobian, but as we see in this case, it's a unit vector, since we are using sort of Cartesian coordinates. So that's what we do. But anyway, this gets 0, so that's obvious. Here it's a little different, but if you remember that this is the normal vector for phase number 2, well, we have the situation that the middle component of the vector field vanishes, while the other two components of the normal vector are 0. So for the scalar product, nothing results. There's no contribution altogether, right? We always have a factor of 0, u squared times 0 plus 0 times -1 plus uv times 0. So it's a 0 flux again, for a different reason now. The reason is, if you look here again, this time the vector field is as I said, it does not vanish, but you can imagine it would look like streaming just somehow along this side face of the cube, okay? It streams along the face, which means neither it streams inward nor does it stream outward. So if there is no flux, the flux is 0 for this part, okay? So let's move on to, now we're arriving at the bottom face of our cube, where we already said, well, just keep it in mind, if possible, we use 0 instead of x, y, z. And that's why we get, here it is, this one, right? V squared for the first vector component, uv for the second, 0 for the last. And this time the normal vector looks like this. So again, the vector field, this time the field vectors are oriented horizontally, but also the bottom face of the cube is in a horizontal orientation, which means again the vector field streams along this face of the cube and does not produce any inward or outward flux. So the result is 0 again. If this is 0, I don't even need to perform the two integrals, of course, they get 0. For the fourth one, it gets interesting. The first time we get a positive flux. Well, we always have to look back. Where does this come from? 1 UV. It just looks a little bit like the radius vector itself. Actually, it is. This is 1 UV as the radius vector, but at the same time, in this case, it is the vector field or the field vector. Why? Well, 1 UV means that the x component gets to be 1. So here, inserting 1 for x, u for y, and v for z, we always get, since this is nothing else than multiplying the radius vector xyz with an additional factor of x. And if the factor of x equals 1, it gets identical to the radius vector. In this case, well, in the sketch, it means that at face number 4, here, the front face, if you imagine, it's a little difficult to draw here, all these radius vectors coming from the origin and, well, pointing to this surface number 4, to the front, okay? It turns out that the vector field itself looks like this in a way. Well, but you would have to, it's hard to draw now, but you may imagine that we really have a visible radiality or divergence of these field vectors out of this front face of the cube. It's a little, geometrically, it's not so simple as it seems. Well, anyway, we get the vector, look here, 1 times 1 squared, yeah, for x, okay, 1 squared. Then 1 times u, which is u for the second, and 1 times v, which is v for the third. So that's not really, it might be confusing, but 1 uv is the same for also here for the field vector, 1 uv. And as you remember, the normal vector will be 1, 0, 0 here. So in fact, the flux contribution is just due to the first vector component, because the normal direction of this phase points, what is it, toward us, right? Yes. And so 1 times 1 plus u times 0 plus v times 0. So 1 results, and 1 is, you could say, the local contribution of the, well, the flux the vector field generates here. And this constant 1 has to be integrated over u and over v, which is simple because integrated from 0 to 1 over a Cartesian variable, well, and this is it doesn't matter which kind of variable, this is a constant 1, so it just gets a factor of 1, and the 1 just stays there. Also, if I integrate over v a second time, it gets a contribution of 1 to the flux. So part 5, well, analogously, but let's just check it all the time. We have v1u to be taken for x, well, v1u for here, for xyz. So we get v squared, v times 1, which is v, and v times u for the third one. And you also remember that for phase number 5, it is here, the normal vector. I didn't even give it, but we can see it here. And 5, this one points to the right, it's 0, 1, 0. So that's what we see here. We see that this vector field, this field vector, I could say, scalar product taken with the normal vector 0, 1, 0, gets a contribution this time of nothing, okay, but in the middle component we get v times 1, which is v. That's interesting because the first time this is a non-constant contribution, just proportional or identical to v. You see that v increases due to the the outside integral from 0 to 1. But on the other hand, we just have to integrate v over u and v in the regular manner by solving this iterated integral, even if it's simple. And analogously, let me shorten this. The same holds for phase number 6. Here the field vector is u squared uv u for similar reasons as before, and the normal vector points upward. And we have a contribution due to the third component only, which is then u times 1. So the contribution is u. And this has also to be integrated over u and then over v. Let's just look at these last two integrals a little closer, because the first three, as we've seen, don't contain anything, so they get 0. The fourth one was trivial because it's a constant 1 integrated twice over a range of 1, so it stays 1 as a flux contribution. So this is number 5 and number 6. What do we do? Well, integrating v over u means this is handled as or treated as a constant. So we just get, well, I'm doing it in detail now. So we just get a linear contribution of v, factor stays there, times variable u over which we integrate, and then to be evaluated from 0 to 1. But this is the same again as to say it's just a factor of 1 referring to u, which comes along, and the v stays there as long as we haven't performed the outer integral. So we still have to perform the integral of v over itself, okay? And then analogously, we get, but here, well, the difference is, in this case, the u variables stands here and the u integration is performed first, so that immediately we have to integrate u to the primitive function u squared half as usual, and then to evaluate from 0 to 1. And then the second, the outer integral over v gets trivial, okay? So you could say here the first step is trivial, here the second step is trivial, but the result should be the same, because here I have still to integrate over v, which gets me v squared half. I didn't write it down because it's simple. And then inserting 0 and 1, the total result is 1/2. While here I can evaluate immediately, getting a 1/2 contribution still constantly 1/2, but then integrated over v, which then gets 1/2 as a result also. So the flux contribution of this vector field on the surface of the cube consists of, well, a contribution of 1 due to the fourth face of the cube, contribution of 1/2 due to the fifth and to the sixth face in both cases. So altogether, we get 1 plus 1/2 plus 1/2, which is 2, exactly 2. So 2 in the units, or well, in mathematical units, the total flux of this vector field on the cube is 2, which means there is a positive flux. So there is some outward radiality of this vector field altogether, if summed up along the surface of this cube. So, and that's really what we wanted to find out. And for the rest of it, let's just bring this to an end. It's just to verify this result by using the divergence theorem. What do we need to this end? Well, we need the divergence of the vector field, which we had calculated before. It's quite simple. And then we have to sum it up continuously over the inside of this closed surface, so over the volume of our cube. And this is quite simply done now in the next step, where we also, well, perform a real volume integral, which is, you could say, a triple integral performed as an iterated integral with 3 steps. And as you see, what we get is, where is it? Yeah, the divergence of the vector field is quite simple. This is the first component differentiated with respect to x, as always. So x squared partial for x gets us 2x. Look again, we've done this before in exercise 9.2, number 5, the second. This was where it was all about rotation, divergence, and so on. I put it here again. The vector field is x squared, xy, xz. And if we take the partial derivative of the first component for x, we get 2x. The second for y, we get x. The third for z, we get x. So in the end, it's the sum of 2x plus x, which gets us 4x. That's actually the local, divergence as defined before of this vector field in any point in space, which by chance just depends on the x position. So summing this up over the whole volume of our cube, just transforming this symbolic, you know that sometimes I use 1 integral sign, sometimes 2 or more. This is the short notation symbolically. And also here, I may replace a volume integral, or I may symbolize a volume integral by a single integral sign, although it's a triple integral in the end. Performing it and setting it up, I have to integrate in the range from 0 to 1 over all 3 Cartesian coordinates, so the x, dy, dz. And this is the term for x. And performing the x integral first, we get the primitive function of 4x with respect to x, which is, of course, x squared half times 4. And then we get 2 times x squared, evaluate from 0 to 1. So this is 2. The constant 2 may even be drawn outside, and the rest of it, the integration over y and z, is just trivial, gets a factor of 1. So 2 remains. And 2 as a total flux is the same result as before calculating along the surface. And this is, again, an impressive confirmation of the validity of Gaussian's, of the Gaussian divergence theorem. So that's it for the whole exercise.